For part two on optimization, we're going to get to the actual question. So just remember for part one, we spent the whole first part just talking about how to figure out that closed interval that we're working on, because that part can be a little bit tricky. And now we're going to talk about the rest of the question. So let me go through with just a step-by-step on how to do an optimization question. So step one, and this is really true for any word problem, just read the question and realize what you're doing. And the way you'll know that it's an optimization problem, we talked about this a little bit in part one, is you'll be asked to either minimize or maximize something. And sometimes that can be very simple and straightforward. It can say find the maximum value of blank or find the minimum value of blank. And other times it can be a little tricky, like our example from part one where I said, what are the closest points together? And you had to realize I was asking you to minimize the distance. But you got to read the question and realize it's an optimization problem. Okay, once you do that, draw a picture. I said if necessary, meaning there may be a picture with the question. You don't need to draw one. It may be a question you don't need a picture for, but I would say that probably most of them do. And then step three is assign variables. So once you understand what the question is about, and you have your picture if you need one, you start putting variables in there. And I said, you know, it's up to you to decide what you want to call your variables. You can call everything X and Y in every single problem if you like doing that. But personally, I think it helps you if you assign variables with meaning. So I said you can use A for area. You might use V for volume or D for distance, things like that. So if the letter represents what it means in the word problem, it's easier for you to figure out the closed interval because you know what you're talking about. Okay, now here's the important part. For step four, you are going to write what we call the primary equation for the thing that you are trying to optimize. So the reason it's called a primary equation is because a lot of these problems deal with more than one equation. You have your primary equation, which means the main one, and then you have secondary equations, which you also use in the problem. But the primary equation has to be for the thing you're trying to either minimize or maximize. So here's a couple examples. Let's say we're doing sort of like an economics question where you're making some products and selling them and you want to maximize your profit, meaning you want to make the most money possible. That means you need an equation for profit. So your equation should say P equals something. Profit equals something. Now let's say in a very similar question, or maybe even part B from the same question, you're trying to minimize your costs. You're trying to make it so you have to spend the least amount of money on your company. That's still optimization, and you would need an equation for cost. So you need your equation to be C equals something, or cost equals something. So whatever you're trying to minimize or maximize, if you're trying to maximize area, you need A equals. If you're trying to minimize the volume, you need V equals. So whatever the thing is you're trying to minimize or maximize, you need an equation for that thing. Now, we have a step that we saw something kind of similar to when we did related rates. Sometimes, not always, but sometimes you need to eliminate variables. For this type of problem, we need our function to be a function of one variable only. So for example, I used profit on the last slide. If you have profit equals and you have this equation that has X and Y and Z in it, maybe you have 3 different products you're making, you need to get rid of 2 of them. You can only have one variable in your problem. It doesn't matter which one. You can leave X, you can leave Y, or you can leave Z, but you can only have one. So you need to find a way to eliminate variables until you're down to just one variable. Now, once you get down to that one variable, we're going to do what we did in part one. We're going to take that variable and we're going to say, okay, what's the smallest that thing can be? What's the biggest that thing can be? And then once you have those 2 numbers, that gives you your closed interval. So remember in part one, I basically gave you some questions and I said, okay, if X is the variable, what's the interval? If Y is the variable, what's the interval? Well, see, we don't know which one is going to be the variable until you do step 5. Once you eliminate variables and you're down to 1, that's the one you're working with, and that's the one you want to do the closed interval on. Okay, so we've done a lot of work so far, but the good news is at this point, it's not a word problem anymore. You have your equation with one variable, you have your closed interval, all of a sudden it's an extreme value theorem question. So step 6 and 7 we've already done. If you need to review step 6 on closed intervals, just watch the part 1 notes again from optimization. And if you need to review on extreme value theorem, which is finding a minimum or a maximum on a closed interval, then watch the 5.1 notes on extreme value theorem. So let's do a couple examples together so you guys can see how this works. So we're going to do another, this is actually a very common optimization problem. You guys will see that some type of this question over and over and over, where like a farmer is building something with fencing. Yesterday we did like 3 walls of a fence up against a building. Today we are doing 3 adjacent rectangular corrals, and a corral is like an enclosed fenced-in area. All right, so our farmer has 500 yards of fencing, and he wants to build 3 adjacent, now adjacent means connected or stuck together, rectangular, so they're rectangles, and then I already described corral, it's like an enclosed area. So basically our picture looks like this. You have 1 rectangle, you have 2, and we're going to kind of stick it together like that, and then you have a 3rd one. So this is what our picture looks like. 3 rectangles all stuck together like that. Now, what dimensions will give him the maximum total area? So let's do this. Let's take one of our rectangles and say it is x by y for our dimensions. And you know, you can use whatever letters you want. Some people like L and W, length and width, for a rectangle. I'll just go with x and y. Now, we want, let's see, okay, so basically let me slow down a little. We've done our first 3 steps. We read the question, we realized we were maximizing, we drew our picture, and we labeled our variables. That was steps 1, 2, and 3. Now step 4 is the primary equation. So what we're trying to maximize is total area. So I need an equation for area. Now area of a rectangle is length times width. That's our formula for area of a rectangle. Now we're doing total area, not the area of each little rectangle, but the area of all 3 together. So the rectangle I'm looking at, the base of it is actually 3x. So for my area equation, what I would have is 3x times y. 3x is the bottom, y is the side. So 3xy. All right, that was step 4. We have our primary equation. Now step 5, we can only have one variable. We can't have both the x and the y in there. So we got to get rid of one of them. So let's go back, and this is where I said this is our primary equation here, but we're going to have secondary equations. Let's do a secondary equation for the total amount of fencing. So I know from the problem that I have 500 yards of fencing. Now let's see how many x's and y's total there are in this picture. I have 3 x's across the bottom, but I also have 3 x's across the top. So that's a total of 6x. Now I have 3 separate rectangles, but if you count up the amount of like vertical fencing in my picture, there's actually 4 y's. There's 4 vertical fences. So that's my total amount of fencing I'm using to create this situation. So we have 6x and 4y. 6x plus 4y, and that needs to add up to 500 yards of fencing. That's my secondary equation. Now remember, I said we did something kind of like this with related rates. We need to use the secondary equation to eliminate one of the variables from our primary equation. Now it doesn't matter which one you choose, x or y. Basically take the blue equation, solve it for either x or y, and then substitute it back into your primary equation. So let's go ahead and, it doesn't really matter, let's solve for y. Let's subtract 6x from each side, and you'll have 4y equals 500 minus 6x. And then let's divide everything by 4. And we end up with y equals, that would be 125 minus, if you reduce it, it's 3/2 x. And what I'm going to do is I'm going to take that formula for y, and I'm going to substitute it for that y right there. That's how you eliminate one of your variables. So what we'll have at this point, we'll have area equals 3x times all of that. 125 minus 3/2 x. So right there, that was step 5. That's where we took our primary equation, which had two variables, x and y. We used a secondary equation to eliminate y, so we have only x. All right, now, let me go ahead and distribute the 3x, because we're probably going to want to do that when we take the derivative anyways. So what I get is 375x minus 9/2 x squared. All right, that's going to be my primary equation now. Now, before I move on, the next step is to find our closed interval. Now, because we eliminated y, that makes x the variable from now on. Forget about y for the rest of the question. So x is our variable. So let's pick our closed interval here. I'm going to say, just like our examples from part 1, the lower bound is 0. The smallest x can be is 0 because real life situation. You can't have a negative number of yards for a fence. Now the biggest x could be is if I had nothing left for y. If I took all 500 yards of fencing and I basically put it on the top and the bottom of my rectangle. But remember, there are 6 x's total. So even if I used all 500 yards, it would still be 500 divided by 6 to figure out each x. And 500 divided by 6 doesn't go evenly. I can at least factor out a 2, so call it 250 over 3. That's my closed interval for this problem. So basically at this point, we're done with the word problem part. We're ready to actually do just like section 5.1. Here is my equation. Here is my closed interval. I want to find the maximum for that problem. So we've done the hardest part. We've converted our word problem into a 5.1 problem. So let's go ahead and do the work now. I'm kind of running out of space. I'll see if I can squeeze it in. Step 1 would be to find the derivative, a prime. The derivative of 375x is just 375. And when I do power rule on the second one, we'll still have the minus. When I multiply by 2, I just get a regular 9. I get a whole number 9, x to the first power. So my derivative is 375 minus 9x. If I set that equal to 0 and solve for critical values, I would have 375, if I add, I would get positive 9x. Divide by 9, and x ends up being, let me pause and calculate, get a calculator and check that. All right, it doesn't go evenly, but it does reduce to 125 over 3. So basically, in order to answer this question, we need to check 3 values. We need to check each endpoint of our closed interval. I need to test 0, and I need to test 250 over 3. And then I need to also test my critical value. One of those 3 is going to give me the maximum total area. So let's clear a little space here. All right, so our equation is 375x minus 9 halves x squared. Now what's going to happen for both of my endpoints, if I do a of 0, I'm just going to get 0. Because remember, what we're really saying, like, if you plug in 0 for x, you can see from the equation, if I plug in 0 for x, I'm going to get 0. The reason is, when I got that endpoint, I was saying, what if y is absolutely everything? And you'd basically just have 4 long fences stuck together, and it wouldn't create any area at all. And the same with the other endpoint. It's also going to equal 0. And you could grab a calculator and plug in 250 over 3 for x and see. It does end up equaling 0 for the same reason. What we're really saying is, what if y equals 0 and we just use all of our fence for x? You would have 2 long fences stuck together and the area would be 0. So the last one, the one I actually do need a calculator for, that would be 125 over 3. And basically, I'm going to do exactly that. I'm going to plug in 125 over 3 here and here, and I will use a calculator for that. Now, that one came out to 7,812.5 feet. So that is definitely the maximum. I mean, it was definitely going to be the maximum anyways, because the other two were 0. But the maximum area is 7,812.5 feet. And just remember, always make sure that you're checking and answering the right question. If I had asked you, what is the maximum total possible area, then the answer would be 7,812.5 feet. But I asked you for dimensions. And dimensions means what is the size of each rectangle. So we already found x. What we want to do is go back and find y. Now, I erased the equation for y, but remember, y was basically this right here. So what you want to do, the first answer to the question is x equals 125 over 3. Now, to figure out what y is, you take your equation for y, and you plug the 125 over 3 into it. So let's go ahead and do that. I'll do a calculator again. And what I get for that one is 125 over 2. So that is going to be your final answer there. And you can convert them into decimals if you want, doesn't really matter. But the idea is the dimensions of each corral should be 125 over 3 feet by 125 over 2 feet, and that'll give you the maximum total area. So you can see that was a long problem. It was kind of tricky, a little difficult, but what we really did is what I told you guys we were going to do. We took a word problem and then we converted it into a regular problem and did the extreme value theorem. Let me do one more example with you guys. So what we're going to do is we are going to create what's called an open top box. Think of it like a tray or like a shoebox with no lid. So you have this box with no top on it, basically. And it's going to be created by taking a piece of paper. I said you took an ordinary 8.5 by 11 inch sheet of paper. You cut equal sized squares out of the corners and then fold the sides up. And we want to maximize volume. So I'm actually going to draw 2 pictures for this one. So first of all, my first picture looks kind of like this. This is my piece of paper with squares cut out of the corners. So I took a piece of paper and I cut a square out of each corner. Then what I'm going to do is I'm going to take each little flap that I created and fold it up and then tape the corners together. And when you do that, you will create that open top box that's described in the question. So you'll have this picture, you'll have this thing that looks kind of like this. So you've created that tray, sort of. So we have two pictures for this. The top one is the piece of paper that I cut the corners out of and folded. And then the bottom is the tray after I fold those edges up and tape it. Okay, then we want to name our variables. Now, there's only one variable in this question, and that's the size of the square. You know, I can cut out a very small square or a bigger square or something like that. So what I'm going to do is I'm going to say x. X is like the side of the square that I cut out. So each corner I'm basically cutting an x by x corner out of, or an x by x square out of. So like if x equals 1, I'm cutting a 1-inch square out of each corner. Or if x equals 2, I'm cutting a 2-inch square out of each corner. All right, so let's now try to apply that to our bottom picture. Now x, well actually let me do it this way first. Let's jump to our step 4. So what we're trying to do here is maximize volume of the box. Now I know that volume of a rectangular prism or a box is length times width times height. Now in my picture, I know one of those. The height of this tray is going to be x. If you look at the picture and you realize that you're folding the flaps up, each of those flaps here that you're folding up become the height of the tray, and that's x. Now for the other two, we have to use the fact that the original piece of paper was 8.5 by 11 inches. So this right here is 11 inches. But that's not part of the tray. The tray is this. So what you have to do, you have to realize in order to find that side of the tray, I took my 11 inches and I subtracted x twice, once from the top and once from the bottom. So the side of the tray ends up being 11 minus 2x. And then for a very similar reason, this side of the tray ends up being 8.5 minus 2x. Because again, you're starting with 8.5 inches and you're cutting two x's, one from the left and one from the right. So this side here ends up being 8.5, I'll call it, minus 2x. Now those three numbers, the x, the 11 minus 2x, and the 8.5 minus 2x, that's your length, width, and height. And if you substitute, what you've done, we'll do x times 11 minus 2x times 8.5 minus 2x. Now what you've done is you've already done the next step. Step 5 is to eliminate all variables and get down to 1. We've done that. We got down to our only variable in the whole problem, which was x. So that part is good. What's hard about this question is it's going to get messy from here on out. This definitely becomes a calculator question. And you guys are going to want to use maybe even Desmos, you'll see, to do a graph. But let me multiply this out first. Let's leave the x for now and multiply all of this out. We have 11 times 8.5, which is 93.5. Then we get minus 22x, and we get minus 17x, and then we get plus 4x squared. So that gives us x times, it would be 93.5, minus, that would be 39x plus 4x squared. And then let's go ahead and distribute that x too. So what we get is 93.5x minus 39x squared plus 4x cubed. Okay, now let's do our closed interval. So what we're talking about, let's go back to picture number 1. We're cutting a square out of the sides, or out of the corners of the paper. Now the smallest x could be would be 0. That's again, I told you that happens a lot in these real life word problems where your lower bound is going to be 0 because you can't cut a negative number out, but you could cut nothing out if you really wanted to. Now, your upper bound, what you have to realize is that the biggest the square can be, it's going to have to do with the shorter side of the paper. So remember, the shorter side of our paper was 8.5 inches. The biggest square I could possibly cut out of that would be exactly half that number. It would be 4.25. Now the reason for that is if I try to do more than, like if I try to do 5 inches, I run out of space. If I cut a 5-inch square out of one corner, then there's only 3.5 inches left of paper for the other one. So basically like half of the shorter side, 4.25 inches, that would be the biggest square I could cut out of this. And this is why I spent a full day just talking about finding closed intervals, because that part is tricky. It's tricky to look at a question and ask yourself what's the biggest and smallest x could be. And in this case, it's 0 and 4.25. Okay, so we are ready for our question. Again, we're at the point where we're kind of done with the word problem. We are now doing this problem right here with 5.1. So let me find the derivative, v prime. That would be 93.5 multiplied by 2, and you would have minus 78x, and multiplied by 3, and you would have plus 12x squared. Now, I need to see where this one equals 0. So what I'm going to do is, this is not like a clean problem where you could use, factoring or anything like that. You could use the quadratic formula, but that would get messy. What I'm going to do instead, I'm going to go to Desmos. I'm going to graph this thing. I told you this is kind of a calculator question anyways. I'm going to graph this thing and look for x-intercepts. So let's do that. So here's the graph of our derivative. What I did is I graphed 93.5 minus 78x plus 12x squared, our derivative. And all I'm really looking for is the x-intercepts. It's a parabola, but I don't need to see the whole thing. I just need to see these 2 points right here. So by floating over them, what I can see is that the first one is, we'll call it 1.585, and the other one is 4.915. Now, those are our critical values because that's where our derivative equals 0. Because remember, we're looking at the graph of the derivative, and where something equals 0 is its x-intercepts. All right, so let's go back to our problem. Okay, so this is where we left off on the problem. We just found 2 critical values from Desmos. One of them was 1.585 about, and the other one was 4.915. Now, if you look at those critical values, and you look at our closed interval that we figured out, the 4.9 is too big. We said the biggest square you can possibly cut out is 4.25 inches. 4.915 is too big, so throw that one out. Don't use that one. It's not on our closed interval. Remember, that was part of 5.1. You're only looking between 0 and 4.25. The answer can't be 4.915 because that's too much. We can't cut that much out of the paper. So basically, I need to test 3 things. I need to test v of 0, and if I plug in 0 for x, I'm getting 0. I need to test the other endpoint, v of 4.25. Now, I won't do the work, but you're also going to get 0 for that. We're basically saying, like, if you cut the corners so that it takes up all the paper, you're just like cutting the tops and bottoms of the paper off, and there's no volume left. There's no tray to make. Or you could actually grab a calculator and plug in 4.25. You'll see the answer comes out to 0. So the last one to test is 1.585. It's definitely a calculator question, so I'll go ahead and I'll do that and come back. And I got about 66.15 for that. So that's definitely the maximum. We were asked to maximize volume. That is the volume. So the answer is 66.15. Since we were measuring in inches and its volume, it would be cubic inches. So the answer to the question is, if you're cutting up that paper and folding it up and making a tray, if you want it to be able to hold the most amount possible, to have the absolute maximum volume, you want to measure each square to be about 1.585 inches. Cut that out of the corners, fold it up, tape the sides like the bottom picture there, and then the volume of that will be about 66.15 cubic inches, and that'll be the maximum volume you can possibly make in that situation. So that's how the optimization questions work. You can see they're not easy, they're not short, it takes a little bit of work to do, but what we're doing is we're reading a word problem, drawing a picture, naming variables, coming up with your primary equation, getting it to one variable, coming up with your closed interval, and then finally, after all that work, that's the hard part, then you go back and you do the 5.1 problem, where you do the minimum or maximum, whatever you're being asked to do, on that closed interval.